Oh, hi there. You might be wondering why I'm inside this room. Well, Earth is currently on fire, and we all deserve some nice refreshments. And now, we're not going to talk about climate change. What we're going to talk about is what's inside in this very cup. Have you ever wondered why the pearls in your milk tea stay at the bottom of the cup and the ice stay afloat? And come to think of it, why do icebergs, which are enormous in size, stay on top of the ocean while small needles sink? What is this sorcery? Well, it's not sorcery at all. It's all physics.
Yes, you're right, Alvie. It's all physics. Hi, I'm Toquero. Let me take you to the most obvious place where we can find the answers to your curious questions. Let's go! Yes, you're right. I am at the beach, perfect for this weather, and most importantly, perfect for this lesson. Have you tried pushing a beach ball under the water? I bet you have. It is difficult to fully submerge the beach ball because of the buoyant force that counteracts the applied force. But how strong is buoyant force? Why do some objects sink while others float? Well, it's certainly not because of size, because of a tiny peso coin sinks while a massive ship floats. The answer to this question is explained by the Archimedes principle.
Archimedes principle.
Archimedes principle states that when an object is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. So now, if we compare a ball and a stone and approximately the same sizes, these objects may occupy the same volume, but the stone weighs much more, so it's much denser than the tennis ball. So I have here a cup of water, a ball, and a stone. So if we compare these two objects, I will drop these two objects and look at the water. So if I drop this stone in the water, the stone pushes the water upward with a force equal to the weight of the displaced water. Since the stone weighs much more than the amount of water that it displaces by it sinks. Meanwhile, a ball displaces a very small amount of water and the air inside is lighter. So as you can see, the ball didn't sink. So So the air inside is lighter than the weight of the water that it displaces. So the buoyant force is what keeps the tennis ball afloat.
How can this principle be applied to ships? Steel is much denser than water, so you would think that massive steel ships would sink, right? Well, think again. Ships are made of mostly hollowed out shells of steel, but most importantly, there is air inside these ships, and air is much less dense than water, which keeps the ships floating.
Let's go back to your first question. Why do these pearls in your milk tea sink while the ice stays afloat? Well, simply because the pearls are much denser than the liquid it is in ice is less dense than water, making it to float to the surface.
Now, we know why those pearls in your milk tea stay at the bottom. Oh, and one last fun thing about this. Did you know that Archimedes yelled "Eureka, Eureka," which means I have found it when he had made this discovery? Hi! We hope that we had contributed to your Eureka moment. Stay curious!